Okay, so hi everybody, and let me introduce you the today's visitor and speaker, Professor KICHEON Kang from the Chonnam National University of Korea. KICHEON has been working as a professor there since 2003, becoming full professor in 2012, and he comes from the work on condensed matter physics, but more recently became more interested in working on quantum foundations, and especially on quantum locality. He has been working both in Korea and some other institutions also in Germany. And today he's gonna talk us about the locality of the Aharonov-Bohm effect and from a quantum electrodynamics perspective. So I thank Professor for being with us today and give him the word.
Yeah, thank you for the introduction. I think the field of quantum foundation is so diverse. So it's my topic is the Aharonov-Bohm effect, which is actually the kind of action at distance when you have some charged particle moving, but there's a magnetic or electromagnetic field located far away, but you still have some kind of physical effect. And this apparent non-locality, I will address how to treat this problem. And actually, I'm from the city of Gwangju, which is located in the south and the western part. Maybe you don't know very well, but it's disappeared. It merged into the bigger provisions like Jeonnam, Gwangju from this month, so that it doesn't exist anymore. But I think if you know the city, the name of the city, I think you know from this the history of Korean democracy, so-called Gwangju Uprising. That's the most well-known historical fact about my city. Okay, go back to physics. So the birth of the locality problem dates back to the time of Newton. By the way, you can ask any questions feel free to ask any question during my talk because it looks more like informal. Yeah? I like that. So for him,
sorry,
yeah.
make a side comment. If you're gonna make questions, please tell me so that I give the mic so that people in the stream can also hear.
Okay, for him, it's a kind of very absurd thing that this gravity is interaction between two distant bodies. So for him, it's that one body may act upon another at a distance through vacuum without meditation of anything else. It's really very absurd thing to him. And he thought that gravity must be caused by an agent, which I think it's inspiring to many physicists later for the later developments like electromagnetism and the theory of relativity, also quantum mechanics. It's kind of continuous source of inspiration. So even the word of act, how to say, an act upon another at a distance is his word, not from Einstein. And what's the locality principle? So locality problem. I mean, basically it's a rough definition. It's the principle that an object should be only directly influenced by its neighbor, its immediate neighbors. So it should be very close in terms of space-time location. And historically, the instantaneous non-local series have been replaced by local ones, like for example, Coulomb force is also kind of non-local it looks like a non-local effect, but it's replaced by Maxwell's field equations. And also this Newtonian gravity was replaced by general theory of relativity in terms of curved space-time. And also the speed at which the influence is transmitted is limited by the geometry of space-time. So special theory of relativity limits the speed at which such influences can travel by the speed of light. But I mean, until this time, everything seems very perfect. But the things got complicated after the appearance of quantum theory. So it's apparently violated in quantum theory. I mean, I think many of you already know very well about this EPR paradox and violation of Bell's inequality, which has been very extensively studied for many years. And there is another thing which I will focus on today, is the Aharonov-Bohm effect. I will tell you about some backgrounds. And by the way, the Schrödinger equation is very local. It's because it only allows unitary time evolution. Okay, what's the Aharonov-Bohm effect? It's a quantum interference under localized magnetic flux, or sometimes localized electric field. So the basic setup is the following. You have charged particles, which is described by the standard quantum mechanical wave function. Then you split the path of the charged particle by 2. Then you apply some localized magnetic flux. The particle never get in touch with the localized magnetic flux. And sometimes the particle can transmit, sometimes reflect, and you get you just plot as a function of a flux and counts. It's just proportional to the probability of transmission. So it's very easily described by Schrödinger equation with this Hamiltonian. But classically, there's nothing, but there appears some interference pattern without any direct contact between charge and magnetic field. That's it. That's the basic theory of Aharonov-Bohm. But if you go into a little more detail, then I mean the reason why is there's some effect by the presence of magnetic field at a distance is the following. I mean, because you cannot eliminate the vector potential A in Schrödinger equation. I mean, in Maxwell's equation, you can eliminate. You can have some vector potential and scalar potential, but it's introduced only for convenience, mathematical convenience. You can convert it into Maxwell's equation only in terms of E and B. And you have some charged particle or some current, the current and charge are influenced only by E and B. But in quantum mechanics, it's different. You can never eliminate A. So there appears some effect mathematically. So you have no direct interaction with B, but you have direct interaction, local interaction with A, vector potential. But the problem is that A is not a locally well-defined quantity, because you can use another A, which under the so-called gauge transformation. It has some very interesting property of gauge symmetry, which is also very important in the development of modern particle theories. And you can use another gauge, then because curl and the curl of a gradient, some scalar function is always 0. So you have the same magnetic field, And you will find what the period of the interference pattern is actually proportional to the value of magnetic flux. And the magnetic flux is also can be written in this way, but you can use different gauges. So the standard concept for this Aharonov-Bohm effect is that only the topological phase is relevant, and the local value of A is not very important. That's a standard picture. And you can ask the question like that. It's just part of quantum weirdness, and cannot specify the space-time location of the interaction. That's a question. So I'll try to go a bit more detail about this question. Of course, you can just say, okay, it's a quantum weirdness, and then, I mean, action, something like action as this. Of course, you cannot send an information, but you have some kind of apparent non-locality. You can say that, but I'll try to be as much real as possible with this problem. So there has been some revival of debates based on semi-classical solutions. Semi-classical means that the particle is treated in quantum mechanics with Schrödinger equation, but the field, electromagnetic field, is treated in classical way. If you see this one, from A is generated by magnetic flux, but usually it's treated in semi-classical vector potential. Of course, it quantizes the Hamiltonian, but the A itself is kind of classical value. Okay, so I mean, there has been some revival of debates. It's quite it's not recent anymore, but I was a part of this debate. I mean, also interestingly, there was some objection by Aharonov himself. I'm not going into detail about the semi-classical debates. Okay, here's my agenda. I'm looking for looking the problem from some different perspective. Let's say interference generated by two independent sources can actually can be used to prove the locality of the Aharonov-Bohm effect. And I will adopt quantum electrodynamic approach, which means that both electromagnetic field and particle should be treated from the scratch, like from quantum mechanical way. And in addition, I will address the problem of so-called fractional spin in anyons, which has some structure of charge-flux composite. Okay, first, what about the interference generated by two independent sources? Okay, it's the following. Up. Up. Okay, just imagine that there are two sources, two wave sources, and I mean, you know, everybody knows that. For example, like two fishermen making waves, generating waves, you get interference. Everybody knows it. As far as the two waves are coherent, but you can see in the real time for this case. But if you do it with the photons, you need a real coherence. But anyway, this is nothing special. As a function of delay, time delay, or phase difference, you get interference of the count or intensity of the wave. So in classical level, this is very well known. But the question is now imagine that you attenuate the source signal. So you cannot attenuate it forever because there's a limit that nature allows, so-called single quantum limit, let's say. But in this case, it's like a photon, the vibrons or something like that. then the detect clicks only single quantum at a time. Then what happens to this quantum limit? That's the question. I mean, I'm trying to make a quiz with my students for them to think about. I mean, actually, if we have some time, then I will give you some 5 minutes. What happens to this quantum limit and why it happens? If there is some interference or not, then you should explain why. But I will give you the answer immediately. Actually, there's interference. There's an interference. You just count they detect single. In this case, single photon. That was first proposed by Mandel group. It's not very much appreciated for some reason. And as a function of delay, there's again interference. Of course, I mean this pile of single photons, single photon profiles. And how to interpret this result is that, I mean, every time you detect the photon particle, we cannot tell in principle the origin of the detected particle. I mean, when there is some indistinguishability, you have to add up the probability amplitude, and then you get the interference. That's a quantum interference. Okay. I mean, let me go a little detail about this. Just imagine that there are two identical atoms. I mean, it doesn't have to be identical. I mean, just need to be indistinguishable photons. The atoms are initialized to superpose state of ground and excited state, and they just wait. And the spontaneous emission of photons will generate this kind of state, superposition of vacuum and a single photon. Then you just detect the photon, and it's very simple exercise of quantum mechanics to calculate the probability of finding photon here is just proportional to intensity of electric field, which is given by these two creation, and that's the analyzed operators of photons. Then you get this interference of this part. Actually, there's a phase difference between two passes. And one thing is needed, that superposition of 0 and 1 is necessary. So there are some limitation, so some constraint on this. Otherwise, you don't have interference. Okay, there's another thing, similar related phenomena, which is the interference of two independent Bose-Einstein condensates. So that's how to say this, dashed dotted lines are profile of a single Bose-Einstein condensate, and actually that's from the group of Wolfgang Ketterle in MIT, which is related to Nobel Prize things. And when they meet, the two independent Bose-Einstein condensates meet, you find some interference pattern. So it's another example of showing interference from two independent quantum objects, which are indistinguishable. But anyway, when I first noticed this effect, I knew this effect about 20 years ago from quantum optics person I was talking. I immediately realized that there's some conflict between theories. Why is that? It's like, I mean, we know that now. I mean, that's actually experimentally verified. I mean, the interference between two independent sources. I mean, but the interference of single particle, you should be careful about it. And now we apply this effect to the charged particle, quantum mechanical, or condensates. Then we can expect the same kind of interference. And now we can add another ingredient, like, for example, magnetic flux. Of course, you can control the interference pattern by changing the by changing time delay or path length. But you can also control the interference pattern by the localized flux. But the problem is that I would like to do experiment to observe the interference as a function of magnetic flux. Okay, you will. I mean, of course, you have some. You expect some interference, but the problem is that, I mean, if you think about the Aharonov-Bohm effect, and there is no closed loop, and I mean, in the Aharonov-Bohm effect, everybody says it's a topological effect, but there is no topology because we don't have any closed loop. Then it means that the flux dependence of the phase shift interference pattern cannot be predicted with the vector potential. Let's say, I mean, let me go on a bit of detail. So you have this simple, again, the Hamiltonian of charged particle. So with the inclusion of vector potential, and the each two charged particles have this kind of state, like in the superposition of vacuum and single particles. Then you calculate the count rate or probability of finding the particles here. Then you get this interference. Now you try to get the flux dependence, but you have this kind of phase shift. But there's no closed loop, which means that if you take another value, if you do the gauge transformation, you get different value of phase shift, which is actually kind of disaster. So, I mean, actually, about 20 years ago, I immediately realized that there's some problem, some inconsistency between some theories. And this means that standard approach fails to describe this local phase shift, I mean, generated by the flux. I mean, there is another thing that, another constraint is that fermions are not suitable for this purpose because fermions cannot be in a superposed state between one particle and vacuum. That's kind of super selection rule. But we have charged bosons. Okay, now let's go. Let me go. Yeah, okay, sure. Yeah.
So basically, I mean, if you argue with this setup, right, to tell you something about physics, right, it has to be somehow realizable, right?
Yeah.
So you're proposing basically two massive things from a different source and whatever to interfere somewhere, right?
How to realize it?
Yeah.
Yeah, I will tell you about it.
The obvious problems with, like, say, like the BC is interference is obviously that the phase is random, right? So it's uncontrolled, right? So where do you get the phase stability from in this meta wave scheme?
So your question was that. I mean, I will tell you about this physical realization. I mean, of course, it has never been realized in real experiment, but I propose a kind of experiment how to realize it in so-called two independent superconductors. So it's okay. So.
If you just take the BC as a reference, right? The phase there is random, right? So you will not never see it.
It's random, but there's interference.
There's interference, but the phase doesn't tell you anything about the delay or whatever.
Right. For the BC, you're right. Yeah. I mean, you cannot you cannot predict the phase. But there's an interference. But in this case, you can control the flux. I mean, initially the phase difference must be random, but after that, then you just after you fix the superconductors, you change the flux, then you can get some interference. I mean, I will address this problem. Okay, so I mean, okay, now I'm going to talk about how to deal with this quantum electrodynamics. And actually, it resolves the locality problem. So, yeah, sure.
So what do you specifically mean by locality problem? So in terms of fields or in terms of vector potential?
In terms of field, I mean, in terms of vector potential, I mean, it's local. But the vector potential is not well-defined quantity in terms of local. I mean, it's not locally well-defined because you can use another.
And basically, if you only allow for interference, right, between closed paths, right, then there's no problem with the potential, right, because you will only ever have closed paths, and there's no problems with defining it.
Yeah, right. But it happens in this open geometry. So, okay, it's a quantum electrodynamic picture of the Aharonov-Bohm effect. So the interaction which is responsible for Aharonov effect is like the charge and flux, magnetic flux. Well, let's say it's a flux tube, or in 2 dimensions, it's just 2 particles. But the idea that the interaction is mediated by the exchange of the virtual photons appears quite surprisingly late. I mean, if you think about the development of quantum electrodynamics, I found it very surprising. I mean, maybe people thought about it, but it never appeared in the literatures before this. I mean, they just tried to use this microscopic derivation of Aharonov-Bohm effect from the QED point of view. And recently there appears some explanation trying to explain the local phase shift from the QED perspective. So, yeah.
So do you know about this paper from Wakamatsu? Because I think both these papers you cited are wrong.
Yeah. I mean, yeah. I mean, there's some technical problem with this paper, but I mean, okay, we can talk about it later. But I don't think that the fundamental thing is not wrong. I mean, yeah. Let me tell you. So there are some debates about this, but okay. Let me continue a bit. And the idea is the following. You start from the Hamiltonian, the microscopy Hamiltonian. I mean, you can derive from whatever you want, from the Lagrangian. And you have charge and flux and also vacuum. And you can write a full Hamiltonian like this. But there are a vector potential and also magnetic field and the radiation. But be careful that the A and B are now not from the flux, but from the radiation. There's no direct interaction between two. So you don't presume that the direct interaction from the beginning. And that's the idea that the interaction should be mediated by vacuum fluctuation, so-called. Now the vector potential can be expanded in terms of creation and annihilation operators of photons. And you do some kind of canonical transformation, which is actually nothing but the changing the basis in the Hilbert space in the very clever way to get rid of first order effect. Then the leading order term, I mean, you get rid of first order. Then the leading order Hamiltonian interaction Hamiltonian is the second order. But there are, of course, self-energy terms, self-interaction terms. You get rid of them. And you have this mutual interaction terms. That's second order. You calculate some, I mean, VA is from here, and VB is from here. I mean, A is then actually interacting with the charge, and the B interacts with flux. And then calculate the matrix elements. Of course, you have to choose some gauge in the beginning, and later I will tell you about this gauge transform in general gauge. And applying the condition in the Coulomb gauge, which has no longitudinal photons, and you get I mean, there's some calculation steps. I mean, the picture is like this. You have one photon is created, virtually created from one source, and it's absorbed by the object. Then you get the second order Hamiltonian, which has the form like this. A tilde is here. You can define it's like an effective vector potential. So vector potential is now somehow derived from the quantum electrodynamics. Of course, question remains that I have not addressed the problem of the gauge dependence. So let's check about the gauge dependence in this problem. So, I mean, it's not the problem of choosing gauge and the semi-classical potential. It's a problem of choosing gauge in the radiation field. I use another gauge in the radiation field in the vector, the photons. You have any scalar function, a scalar field can be used for this. And now this one generates only longitudinal modes because there's a gradient scalar function. So, but this one, I mean, if you check the matrix elements, this flux radiation interactions involves only transverse photons. And this one, I mean, this delta H2 is just I mean, when you do different gauge, you have some additional contribution. And this additional contribution comes from here. And this involves only longitudinal photons. So actually, it never appears. So it goes to 0, which means that if you use for any gauge, your Hamiltonian is, your interaction Hamiltonian is well defined. You cannot use different value of effective vector potential. You are allowed to have different gauges, but for the effective vector potential is well defined, locally well defined. I think that's my solution. And here's the experimental proposal. I mean, the thing is that now I fixed, somehow I get the well-defined vector potential, effective vector potential derived from this QED. Then you can do an experiment. Now you can predict the experimental pattern. Okay.
So in your calculation, do you get the right sign of the phase shift?
Yeah.
You get the correct sign, or the
yes, I get the right sign of the phase shift. Okay. Yeah.
Do you also have 3 terms then, or is it?
What?
So I mean, in these other calculations, what happens is that you have like 3 terms which have basically.
I mean, other papers.
Yeah.
I mean, there's some mistakes, I think.
Yeah. And whatever. So if you forget terms, you get the wrong sign and whatever. But you also have this kind of similar qualitative thing that you have multiple terms which look similar, but only one survives in the end, kind of.
Well, but no. Actually, there's no multiple counting. So here, I mean, there's no sign problem here. I mean.
And this is in this 2022 paper, right?
In my paper, yes.
Okay,
yes.
I'll take a look.
It's my things, so yeah. I mean, there's something, I think there's a kind of technical, I mean, he has this 2020 papers, has some mistake in the vectors. I mean, that's one thing commented from, I know this, but, I mean, yeah. I have checked this, so. Okay, anyway, the conclusion is simple. So effective interaction is gauge independent, gauge invariant. Now you can do some prediction. You can have definite phase dependent and flux dependence of interference pattern. So actually it was proposed earlier by myself. I mean, I mentioned that fermions are not suitable for this experiment. You should use bosons, but charged bosons, there's a physical example, very good example is the superconductor, BCS state. Roughly speaking, it's a kind of ground state, let's say BCS ground state, and with single Cooper pairs. And this is boson. So you can use this kind of superposed. I mean, it's in principle, it's already superposed state. BCS ground state already this kind of state. Then you have two superconductors, and they are connected. Of course, there's some stochastic random phase for initial value. But now the thing is that you change the value of flux, then you get the current, let's say current, because it's a probability of finding particles here, and you get this interference pattern. Delta phi predicted by this one. I mean, it depends on the geometry. I mean, if you close the loop, then you get the Aharonov-Bohm phase. Then, I mean, there's some process which is called Andreev reflection, but that's just process converting a Cooper pair into two electrons. But I'm not going into detail about this one. And then you can measure the gauge invariant local phase with this geometry, with open loop. And I mean, this is technically challenging to make two independent BCS states. That's, I mean, you can imagine several different types of setup, experimental setup, which I propose. But this one is the simplest, just to measure just current. But the problem is that it should the current should flow forever. In reality, it's not possible. You have to connect to the circuit somehow. I mean, I'm not going into the technical details for measuring the phase. Okay, question up here. Then, okay, I will. No, it's superconductors. With electrons, not possible.
Yeah, but I mean, there was something about converting a Cooper pair into two electrons.
Yeah, that's so-called Andreev. I mean, I did not include it, but it's so-called Andreev reflections. I mean, of course, I mean, if you know the physics about superconductors, I mean, there are gaps. So below gaps, there's the quasi-particle single electron cannot tunnel. But there's a process so-called Andreev reflection. So I mean, from the normal side, you can the electron can go to the superconductors. If the barrier is reflectionless, then it should go into the superconductors. But there are gaps. There's no quasi-particle electrons are not allowed to tunnel in. But you can have some literal reflection by hole. That's the so-called Andreev reflection. So the net result is 2 electrons are converted into the condensates. That's called Andreev reflection. So always 2 Cooper pairs are involved. I mean, of course, in the normal side, it's 2 electrons. I mean,
they should then somehow interfere, right?
Yeah, I mean, interference.
So you have those states current interfering, right? You measure something, right?
It's just a measure current.
Okay, and then in the next measurement, how is it clear that they will have a stable phase to the first one? How is this guaranteed?
I mean, once you get the phase, then you change the flux, I think. I mean, this, I think, a bit tricky. But of course, the initial phase should be stochastic, like Bose-Einstein condensates. But once you, let's say, collapse, let's say, I mean, if you once measure the current and then you connect the 2 superconductors, then the intrinsic phase difference is fixed. I mean, initially, it was initially stochastic. Then you change the flux. Then
you basically have many copies of them, and so your initial copy kind of gives you initial value for the phase, and then the other copies will give you something different depending on the flux.
But once it's connected, so you assume that. I mean, to be honest, you should assume that that the different copies should have the same value. So. Okay, where I am. So, okay. So let me go a bit. I mean, this is a bit different problem, but which is very closely related to this QED approach to Aharonov-Bohm effect, which is the so-called fractional spin in anyons. I mean, the anion, I mean, there are some very funny, interesting object in 2 dimensions. I mean, in 3 dimensions, the spin of any particle should be quantized in unit of integer or half integer. This is given from the symmetry of our space. But in 2 dimensions, it's different. It may have some fractional value. It's called anion. And the basic thing is the following. So you're in 2 dimensions, you have charge-flux composite. It's actually exactly the Aharonov-Bohm, but now some stationary composite particle, let's say. You have the same in this Hamiltonian. Then now your angular momentum of this composite system has this eigenvalue, which has any arbitrary value aside from this quantized angular momentum. But you can interpret it in terms of reflection symmetry broken, because the all chiral symmetry. I mean, it's because there's flux pierced, then it has broken symmetry. I mean, going counterclockwise and clockwise is different. And this so-called fractional spin is the foundation of fractional statics. We have bosons, should have bosons or fermions in 3 dimensions. That's strict constraint. But in 2 dimensions, you have some more freedom, and which has been experimentally observed recently. But I have different question. Here I got some question. So, but the problem is that now you treat the composite particle as an isolated object in free 2-dimensional space. I mean, free 2-dimensional space has rotational symmetry, also reflection symmetry. I mean, this kind of simple exercise. You have fundamental O2 group, which has rotational and reflection symmetry. and you have, I mean, this is a rotational operation, and angular momentum appears here, and after one turn, you should go back to the same state, which means that alpha should be real value. I mean, in this case, it's consistent with the anyons because alpha is arbitrary, but now impose rotational symmetry. Then you change the direction, then you should have minus of this one. I mean, but the two sets should have the same values. Otherwise, I mean, symmetry is not preserved. So in the presence of a reflection symmetry, the only allowed values of alpha is 0 or 1/2, which means that also in 2 dimensions, for isolated objects, you impose free space symmetry of rotation and reflection. You should get the quantized value of angular momentum. But it's somehow in tension with a fractional spin. I mean, spin here is because it's intrinsic angular momentum. So how to resolve this inconsistency is my question. Okay, I mean, the first thing you can think about is the field momentum. There's a field momentum, so you can also get some angular momentum. I mean, the field angular momentum can be written in this way, but here electric field is generated by the charge. The magnetic field is localized here. You have some field momentum along this direction, but there's exactly opposite momentum, which is so-called hidden relativistic mechanical momentum. I mean, if you want, I can explain later, but let's say it's, fully relativistic effect, but you don't have any momentum, which is in good agreement with our insight that stationary system cannot have a momentum. So the net momentum is 0. Also, angular momentum is 0 for this from this perspective because it's located at the same position. So this paradox remains unresolved. And okay, here is a bit extension or generalization of quantum electrodynamics approach. Again, the two-body interaction is not given a priori. It's mediated by the vacuum electromagnetic field. Now the difference is that both particles are considered moving because we now treat the two particles on the same foot. And I have, of course, the A and B, all the potentials and electromagnetic fields are from the radiation, not from the other particles. And you get this different components of interaction Hamiltonian, and all derived from this four potential quantized radiation field. Here I write A is different from the effective vector potential I wrote before, but this is related to hidden momentum, which plays very similar role as a vector potential in this case. Sorry, here this large M is mass of flux, small m is the mass of charge. Now I use the standard perturbation theory, and perturbed state involves, the two components actually come into play, and these two static potential, like this Hamiltonian and this interaction Hamiltonian. And okay, it's some calculation. You need some calculation. And okay, let me tell you just conclusion. I cannot use the definition of the usual classical field angular momentum to explain this one, but I adopt a different angle from the Noether's charge. I mean, you have symmetry, and then if there is a symmetry, there's always conserved quantity, which is another charge. I mean, I can derive the two components of the angular momentum, which is kinetic part, and also interaction part. The interaction part is given by these two terms from field moment. I mean, in terms of classical electrodynamics, it corresponds to field momentum and relativistic momentum, mechanical momentum. And I can get the result that the expectation value of the kinetic angular momentum is fractional. But there's another part of interaction angular momentum generated by these two terms. Actually, one thing is located here and the other is located here. It generates angular momentum, and the expectation value is exactly compensating the minus this fractional value. And the net angular momentum is strictly quantized, and then we get this integer quantization rule preserved, restored. But what's the fractional? I mean, you can interpret this fractional spin of anyons in different way. It just corresponds to the kinetic part of the composite particles. Okay, I mean, you can think about the semi-classical theory, but in this case, R cross A introduces gauge dependence, which is not suitable for explaining this. But in quantum electrodynamic formulation, I can get the exactly gauge-invariant angular momentum. Just in the same reason why I mentioned for explaining the Aharonov-Bohm effect. This is the open loop geometry of interference. So consequently, I mean, this one is from the beginning, it's a gauge-invariant quantity. And the intrinsic interaction angular momentum is gauge-invariant. Okay, why standard classical field momentum fails in 2 dimensions? Actually, its classical field angular momentum is written in this way, but from the Noether theorem, you can write in this way. I mean, the two things are equivalent in 3 dimensions, but in 2 dimensions, you can there are some additional boundary terms, which is that kind of tensor, but this scales like 1 over R, which does not vanish at infinity. So you cannot take both. So somehow this indicates that you should choose this Noether's chart, Noether's theorem. Otherwise, it makes trouble. Okay, I think I can, briefly explain. So it's a kind of Gedanken experiment. It's an extension of Feynman's disk paradox. I mean, how weird. I mean, Feynman introduced this paradox, how weird is the electromagnetic field momentum. The things are like the following. So, I mean, here I introduce some quantum mechanical ingredients with also inclusion of radiation field. So in 2 dimensions, the flux is thought to be generated by 2 counter-rotating charged loops, the plus charge and the minus charge. They together generate the flux. This is because initially it has a fractional kinetic angular momentum. Now, just wait, and there is small friction or radiative damping, which causes an adiabatic switch of the flux. Then eventually it would rest, it would stop rotating. Then we know that Faraday induction imparts exactly plus value of this to the external charge, then should rotate, should stop rotating actually. And loops, because of radiative damping, the loops may cause transfer angular momentum to the vacuum via photon emission, but only in units of integer multiples of Planck constant. Which means that the final state has an integer angular momentum of this integer value from this integer n and this integer n. It's in turn means that the initial state must have also strictly quantized angular momentum. I mean, this means that this quantization of angular momentum is not just for canonical one, but physical angular momentum should be quantized in units of integers, ignoring the intrinsic speed of each particle. Okay, I think it's time to conclude. I mean, this is conclusion for this charge-flux composite. I mean, the bottom line is that the exotic statics, fractional statics of anyons do not require the abandonment of fundamental spatial symmetries when the vacuum electromagnetic field is properly taken into account. Somehow the fractional value is hidden, which compensates the kinetic part. Okay, let me summarize. I have talked about this interference of single particles with two independent sources can be used to demonstrate the quantum locality of the Aharonov-Bohm effect. And this quantum electrodynamic approach resolves the question of the locality in the Aharonov-Bohm effect. And I also explain about this fractional angular momentum quantization. And thank you for your attention.
Okay. Questions?
So if your proposed interferometer, right? So you would want to distinguish kind of local from topological. Is that right?
Yeah, yeah.
Because what you measure will still be a gauge-invariant quantity,
yeah,
right?
Sure.
So this problem of being open loop and A not being well defined will not be a problem anyways, right?
In open geometry, it makes trouble because you cannot.
But I mean, your proposal is an open geometry, right?
Yeah,
but you will not see, you will still not see anything not invariant.
Sorry.
So I mean, your interferometer that you propose, right, will still not be able to observe a gauge non-invariant quantity.
No, I mean it's exactly observed gauge invariant local phase, and the local phase is gauge invariant. That's my prediction. So it wouldn't make any.
The one thing you would say is that A is not.
I mean that from
right?
the
right. So
from the semi-classical theory.
So people then could say, oh, I have an open geometry where I show, I don't know, that I can measure a gauge non-invariant quantity, right? But in that sense, your setup is still not open enough to see anything.
Open enough? What do you mean? I mean, you can make open. I mean, in, geometries. What do you mean?
For me, there are two questions, right? So is it a local interaction, which in this context means that it doesn't have to be spatially closed, right? So I think this is, and I think your setup, well, there's certainly problems, but I mean, in principle, you might be able to devise such an experiment where you can distinguish local gauge invariant quantity from topological phase shift, right? But then the other question is whether the Aharonov-Bohm effect is a gauge non-invariant thing, right? And even if in this scheme you will not be able to see that.
For the closed loop, I mean nothing. I mean, the two different pictures give the same result for the closed loop geometry. So it doesn't make any gauge non-invariant quantity, of course. But the problem is that if you have, I mean, it should be the interferometer should be open to check if the locality plays some role. I mean, with the standard vector potential theory, you cannot predict the interference pattern. So if you measure something here, then it says it's exactly you kind of prove the locality of the Aharonov-Bohm effect. And because in the standard theory, you cannot predict anything for this setup. I mean, it's not topological. It's because the interaction is space-time local, well-defined.
Okay, so then my last question is, there are these papers about time-dependent Aharonov-Bohm effect, right? Which I think points at the very similar question, right? So can I do my spatially closed interferometer, right? But I pulse the flux such that it's not well, it's when they open the loop, right? There's no flux, but once they're fully separated, there is a flux. So it doesn't enclose the flux anymore, right? So I think it points at the same question.
Yeah.
And I think in these papers, I don't know them well, but there are some problems with something time dependent. You have electrical fields popping up, these kind of things.
Yeah. You should be very careful about this time dependent problem. So there's additional ingredient is the Faraday induction. It should properly take into account this one. Otherwise, sometimes I see that they give the gauge dependent results, and somehow they didn't take notice of this. I mean, it's more complicated problem. So.
This is also a time-dependent version, right?
No. I mean, this one is not time dependent. I mean, just. Of course, in reality, you have
two quantum states, right? And you take part of those quantum states initially, right, and measure their relative phase, but the rest you leave unchanged, right? And then you turn on the potential or the flux, right? And then you measure again, right? So in a space-time way, right, you still have a closed loop.
Yeah.
So it's kind of time dependent.
I mean, then also Aharonov-Bohm effect is if you try to measure, is time dependent because every time you should change the flux. So the basic thing is that you apply only dish bias. You just wait. You do not change anything. Of course, you should change flux very slowly in reality. It's also necessary to observe Aharonov effect. So,
quantum states are still alive when you turn on the flux.
But right? That's a BCS ground state.
Yeah, no, but you have them, right? So so you measure them. They have a well-defined phase, and then you turn on the flux, right? Which means this time-dependent effect pops up in your.
Right. Yes. Initially, yes. Then after that, you establish this some definite phase difference. Then you change the flux, additive way, of course. Yeah.
Okay. Any other question? No, then let's thank again the speaker.
Thank you.
By the way, Professor Kang is going to be here also tomorrow, right?
Yeah.
So if you want to meet at some point to discuss anything, he will be with us also for the next day.
Yeah, I'm interested in quantum foundation in general, so welcome. So, thank you.